6.1 Estimating with finite sums. Distance traveled. We know why a mathematician pondering motion problems might have been led to consider slopes of curves, but what do those same motion problems have to do with areas under the curves? Consider the following problem from a typical elementary school textbook. A train moves along a track at a steady rate of 75 miles per hour from 7 a.m. to 9 a.m. What is the total distance traveled by the train? Here we have the miles per hour, the velocity graphed, and we're assuming the train is moving at a constant rate, 75 miles per hour. And then on the bottom, we usually graph time, so from 7 to 9. Now we can find out distance traveled by dimensional analysis. We have 75 miles per hour, and then if we want to find out how far the train went, we can multiply this by the 2 hours that it traveled from 7 to 9. Well, the hours would cancel, and we find out the answer is 150 miles. Well, as it turns out, doing this dimensional analysis is the same as multiplying the base times the height. So the base is the 2 hours, and the height is the constant velocity. That would be 75. Well, if the distance is the area under the curve, then couldn't we do the same thing if the velocity is not constant, if it's changing? And what we do here is we just break this up into tiny little rectangles. And no matter how small the rectangles are, there's going to be a little bit of error. Imagine if we had a bigger rectangle right here and then another one next to it. Well, the area under the curve, there would be some missing area right here. But then with calculus, if we add up an infinite amount of rectangles, then we get the area exactly. And that's kind of where we're headed with this. So yeah, we can find the exact area if the velocity is constant, but what if it isn't? That's where calculus comes in. Would the area of this irregular region still give the total distance traveled over the time interval? Well, sure it would. It's area under the curve. Newton and Leibniz, and actually many others who have considered this question, thought that it obviously would. And that is why they were interested in a calculus for finding areas under the curves. They imagined the time interval being partitioned into many tiny subintervals, each one so small that the velocity over it would essentially be constant. Geometrically, this was equivalent to slicing the irregular region into narrow strips. As a matter of fact, we're going to cut it into an infinite amount of strips, and then you get the exact area under the curve, each of which would be nearly indistinguishable from a narrow rectangle. They argued that just as the total area could be found by summing the areas of the essentially rectangular strips, the total distance traveled could be found by summing the small distances traveled over the tiny time intervals, which means that if you add up all the areas of these rectangles, you're going to get the total area. Finding distance traveled when velocity varies. A particle starts at x equals 0 and moves along the x-axis with velocity t squared for time t greater than or equal to 0. Where is the particle at t equals 3? So in other words, how far has the particle traveled after 3 seconds or hours or whatever we're using? But the velocity is going to vary. It's not going to be constant. Let's split the area under this curve, which is going to be the distance traveled, into 3 partitions, and we will use LRAM. In other words, the left side of the rectangle is going to touch the curve. And with the Smartboard software, I have nice tools for that. I can grab a rectangle, and we're going to make a rectangle so that the left side is being hit by the curve. Well, this has an area of 0. And then we'll start where the next one, where the first one left off, and we'll make one length across, and then the left side is going to be hit by the curve. And I didn't quite get that far enough over, did I? That's all right. They should touch each other. And then the third one is right here. We have cut the area under the curve into 3 partitions, and you can see with just 3 rectangles there's a lot of missing area. But we can reduce the missing area by making more rectangles. But for now we're just looking at 3. We have f of 0 times 1, a base of 1, and then the height is the function value at 0, plus f of 1 times 1, the base is 1, the height is f of 1, and then we have plus f of 2 times 1. And we're using f of 2 because that's the height of this rectangle. It's hitting where f of 2 hits. Well, f of 0 into the function is 0 squared. That's 0. So we have 0 times 1 plus 1 squared is 1 plus 2 squared is 4. We have 0 plus 2 plus 4. So we're saying the area under the curve, or the distance traveled, is 6. Let's find the area under the second curve using 3 partitions, but this time we'll use midpoint rectangular approximation method. Let's grab the rectangle tool. And we're going to start our rectangle to the left, and we're going to raise it until the curve would hit the middle of the rectangle. So about right there. Then we'll start where that one left off and raise it until the curve would hit the middle of this rectangle. About right there. And then finally the third one, I got to go up until it would hit the middle. So I got to raise it up a little bit more, about right there. Well, this one has a little bit of area missing, but it has some extra area. A little missing here and a little extra above the curve. And so this one's going to be a decent approximation of the actual area under the curve. Well, now we have f of 0.5, because the height now is right where the function is at 0.5 times 1. The base is still 1. And then we can do base times f of 1.5, and then plus 1 times f of 2.5, because that's where the function is hitting the rectangle. So let's get 0.5 squared, and all these are times 1. So we have 0.5 squared plus 1.5 squared, and then plus 2.5 squared. All of these times 1, of course. So 8.75. 8.75. Now on the last one, we're going to do right rectangular approximation method. So we're going to do 3 rectangles, and we're going to raise this up until the curve would hit the right side of the rectangles. So there's the second one, and here's the third rectangle, and it's going to go all the way up to the top. Well, now we have 1 times f of 1 right here, f of 1, plus 1 times f of 2, 2 up here, that's the height of this rectangle, and then plus 1 times f of 3. And all these are times 1, and we're squaring x, so we have 1 plus 4 plus 9. 9 plus 4 is 13, so we have 14, but that's definitely an overestimate because we have lots of area that's actually above the curve. Let's do the same thing, except we're going to cut this into 6 partitions, and we're going to do left rectangular approximation method. So here's where the first rectangle touches the curve on the left side, and then the second one is right here. Third rectangle touches the left side right there. Fourth, and then the fifth rectangle, and finally the sixth rectangle is right about there. Well, now to find the area, we have to find all of the bases are 1s. So 1 times f of 0. And remember, this is f of t equals t squared, plus 1 times f of 0.5, plus 1 times f of 1, plus 1 times f of 1.5, plus 1 times f of 2, plus 1 times f of 2.5, and that's actually the last one. We don't have one where we're going to use f of 3. So that's 1, 2, 3, 4, 5, 6 rectangles. We need 0 squared is 0, plus 0.5 squared, plus 1 squared, plus 1.5 squared, plus 2 squared, plus 2.5 squared. And the area is 22.5. Of course, that's going to be an underestimate because we have little pieces of area that are not counted for. Graph the region defined by the graph of f of x equals 4x minus x squared and the x-axis from 0 to 4. Partition 0 to 4 into 4 subintervals and show the 4 rectangles that LRAM uses to approximate the area of R. So we have left rectangular approximation method. Calculate the same using the RAM program and calculate for 10, 50, 100, 500 subintervals. So the first thing we're asked to do is graph this. Well, we can take an x out. That's 4 minus x. So the zeros are 0 and 4. So here's 0 and here's 4. And this goes up to a height of 4. Now we're supposed to partition this into 4 subintervals using LRAM. We start on the left side, and the first rectangle has an area of 0. Then we go up, touch the left side, and here's our second rectangle. This one is going to go all the way up to the top and touch the left. And then this last one touches right there and goes to the right. So we have 1, 2, 3, 4 rectangles, and we need to add up the areas. Well, we have each of them is a base of 1 again. We have 1 times f of 0 plus 1 times f of 1 plus 1 times f of 2 plus 1 times f of 3. And that's going to be the last rectangle. We actually don't use f of 4. F of 4 would be down here at 0. When we plug 0 in, we get 0 plus. When we plug 1 in, we get 4 minus 1, that's 3. When we plug 2 in, we get 8 minus 4, that's 4. And then when we plug 3 in, we get 12 minus 9. 12 minus 9, that's 3. So we get 6. We get an area of 10 square units. We're asked to calculate the same value using the RAM program. I have to use a little different calculator for this, so I've brought up the one that actually has the program on it. And so we're going to go to Program. Actually, we're going to not do that first. We're going to go to y equals, and we're going to put in 4x minus x squared. We need that in y1 because our program uses y1 to do all its calculations. Then we go to Program, and we go to the RAM program. Go ahead and run it. The left point is we're starting at 0. The right point is we're ending at 4. The number of subintervals is 4. And it says that the left is 10, and it's kind of cut off a little bit. But left is 10, and that's exactly what we got. Now it says calculate for 10. I did that. 50, 100, and 500. So we can run the program again. RAM. Enter. Left point is 0 to 4. And this time we want 50 subintervals. The right side is 10.6, or excuse me, the left is 10.6624. 10.6624. Let's run the program again. We're going from 0 to 4, and we have 100 subintervals. And let's run the program now. And we get 10.6666. I believe that's a 5.6. You can see it's kind of cutting it off. So for 100, we get 10.667. And notice how the more partitions we have, the more this is starting to converge together. All the answers are starting to become the same because the more partitions we have, the more accurate each of these are going to be. Well, now we're going to run the program. RAM. Enter. We have 0 to 4, and we have 500 subintervals. Now this is going to take a long time, but through the magic of editing, it will seem like it goes pretty quick. But if your calculator is taking a while to find this answer, don't be surprised. Now we have 10.666624, and this one to 3 decimal places is 667. So pretty sure that the answer is 10 2/3. Example 3, estimating the volume of a sphere. Estimate the volume of a solid sphere of radius 4. Let's start out with a circle, and notice how we have this top curve here and the other half of the circle. And the equation of that circle is the square root of 16 minus x squared. Now think about a sphere and cutting that sphere into 1, 2, 3, 4, 5, 6, 7, 8 cylinders. Now of course when we draw the sphere, there's going to be some volume that is missing. So this is going to be an underestimate. But notice how the radius of all of these, the radii of all of these cylinders, follow the curve of the circle. So now the whole concept here is if we take the volume of all of these cylinders, a known volume, and add them up, that's an estimate of the volume of the sphere itself. So the volume of the cylinders is pi r squared h. But the radius of all the cylinders, they're changing, but they're following this equation right here. So we can change this to volume equals pi times the square root of 16 minus x squared squared. And then the height of all these cylinders is the change in the x. So times the change in the x, or the number of subintervals. Well, our RAM program will calculate the height when we say we're going from -4 to 4 and we want 8 subintervals. Let's go to the calculator. Well, no, let's not go to the calculator now. Let's simplify this. We have pi times 16 minus x squared. The square root and the square cancel each other out, and then times the change in the x. Let's go to the calculator, and we will enter in pi times 16 minus x squared. So we have pi times 16 minus x squared. And now we will run the program. So we have program, go to the RAM program, run it, and we're going from -4 to 4. And let's, instead of going 8 subintervals, maybe we try 100 subintervals, so we'll get a good estimate. Through the magic of editing, we'll make this see, oh, hey, I didn't even need editing. It goes pretty quick. Now we're using, does it say, estimate the volume? These are all fairly close. So we're looking at a volume of 268.0, if we use the mid one, 096. Well, we know the volume of a sphere. It is 4/3 pi r cubed. And that's equal to 4/3 pi times 4 cubed. Let's see what that answer is. So let's, I guess we're done with this anyway. 4/3 times pi times 4 cubed is 64. We get an answer of 268.083. So it's very close estimate using 100 subintervals.